Hi everyone and welcome back. So today we're going to be talking about Hamiltonian systems. This is following up on our discussion last time of conservative systems. Hamiltonian systems are one particular kind of conservative system, a special class. So they work this way. We start with the system of first order autonomous differential equations, nonlinear usually. X prime equals f of xy and y prime equals g of xy. So let me just give you a warning now. You should be getting some very strong sense of deja vu very soon for exact equations. It's going to seem very much like exact equations. There's a strong connection here. So this is going to be common themes. All right. So what makes it a Hamiltonian system is if there's a function h of xy called the Hamiltonian that has the property that the partial derivative of h with respect to x is equal to negative g, so negative the equation in the second one, and the partial of h with respect to y is equal to f. For it turns out that if you have a Hamiltonian, so a function whose partial with x is this function, partial with y is this function, then the Hamiltonian function is always a conserved quantity, and you get this conservation law, h of xy equals c for solution curves xy. This is always going to be a conservation law. To see why this is, you would take a solution and calculate the derivative of h of x and y with respect to time. So let's do that calculation real quick. We want to take the derivative of h of x of t, y of t, with respect to t. So how does that work? Well, first you take the partial of h with respect to x times, chain rule, dx dt, plus the partial of h with respect to y times dy dt. All right, but we already have, because this is a Hamiltonian, dh dx is minus g. Because this is a differential equation, dx dt, from our first equation up here, dx dt is x prime is equal to f. In the second term here, because it's a Hamiltonian, dh dy is f. And dy dt from the differential equation is g. So minus g times f plus f times g, that equals 0. So since the derivative of h with respect to t is 0, that means that h is constant with respect to time. All right, so we've got ourselves a conservation law if things have this particular form. So let's look at an example. This is our pendulum system again with g equals L. So we have x prime equals y and y prime equals minus sine of y. So this is a Hamiltonian system where our Hamiltonian is 1/2 y squared minus cosine x. How can we see that? Well, all we have to do is take a couple of partials. We take the partial of h with respect to x, and we get, we get the y part is 0, and we get minus sine of y, which is, we get positive sine of y, of course. Come on, I gotta know how to take my derivatives. Right, so we get positive sine of y, which is the negative of g of x and y, which is negative sine x, negative, negative. And the partial of h with respect to y is y, which is equal to f of x and y. So that matches the definition of what it takes to be a Hamiltonian. Let's just take a little quick check. Yep, we have derivative with respect to x is minus g, derivative with respect to y is positive f. All right, we're in business. What if the signs were switched? If the signs were switched, you're okay. The Hamiltonian is just the negative of what you were trying. Okay, so it's great to be able to say, oh, this is a Hamiltonian system when someone hands you a Hamiltonian. That's easy enough. But what if you are just given a system and you want to know whether it's a Hamiltonian system? How do you find the Hamiltonian? How do you know that it's worth going looking for one in the first place? This is the same question again that we asked with exact equations. How do you know if an equation is exact before you go looking for the solution type? Well, we have a nice theorem that tells us what to do. So if we have a system like we had before, x prime equals f of x and y prime equals g of x and y, and we assume that f and g are continuous and have partial derivatives that are continuous, right? All of the partials, f with respect to x and y, g with respect to x and y, everything's continuous. Then this system will have a Hamiltonian if and only if the partial of f with respect to x is equal to negative the partial of g with respect to y. So you basically take your x equation, take its partial with respect to x, take your y equation, take its partial with respect to y. If those are negatives of each other, you've got yourself a Hamiltonian system. How can we really tell that that's the case? How can we justify this theorem? Well, let's do a little calculation here in the bottom just to kind of bring this home. So let's see. Let's look at the partial of f with respect to x. Well, because of the definition of the differential equation, this is the partial with respect to x of f, but we know that f is equal to the partial of h with respect to y. So what we have here is the second partial of h with respect to x and y. But we know from multivariable calculus that mixed partials are equal to each other. So if we go with the second derivative of h with respect to y and x in the opposite order, that'll be the same. That's equal to the partial with respect to y of the partial of h with respect to x. And because it's a Hamiltonian, that is the partial with respect to y of minus g, right? Because partial of h with respect to x is minus g. And so we get minus partial of g with respect to y. So that's one direction. We get exactly the equation that we were told we would get. And it works in the other way as well. If this happens, then you can construct the Hamiltonian. How do you construct the Hamiltonian? Well, you do it by looking at the definition of Hamiltonian and doing some partial anti-differentiation and comparing, just like we did with exact equations. So that's how we recognize a Hamiltonian system. We just have to take a couple of partials and see whether they have the opposite sign of each other. All right, so this feels like time to do an example. So let's do two. Let's do two examples. So these are some problems taken from the textbook with a little bit of modification by me. So these are problems 6.3.23 and 25. And what we're asked to do here is to determine whether each of these systems, right, we have two systems, one here and one here. We're asked whether each of these systems is Hamiltonian or not. And if it is Hamiltonian, find the Hamiltonian function. Find h. All right, so let's begin on the left. So I would encourage you at this point to take a pause and try this out for yourself. Check each of these systems, see if it's Hamiltonian or not, right? And then come back. So I'll give you a second now, a little pause here, and then hit play again once you figured it out. All right, hope you actually did that, and we're going to do it, and I'll go through it now and make sure our work matches up. So with this first system, we want to check whether we have a Hamiltonian system or not. So what we need to do is we need to take the partial of f with respect to x. So that means taking the first equation and taking the right-hand side and taking its partial. So using the chain rule, when we do this, we should get minus 2y cosine of 2xy minus 1. All right, so hopefully that makes sense. And then we also need to take the partial of g with respect to y. And in that case, we'll get 2x cosine of 2xy plus 1. Now let's see. A lot of things match up. We need these to have the opposite signs, minus 1, plus 1, good. Cosine, those match. We got the signs, got the 2's, but here we have a y and here we have an x. So these mess it up. We can pick a point xy where these won't be opposites of each other. So this is not Hamiltonian, right? And because it's an if and only if statement in theorem 6.2, we can be sure that it's not that we're just missing something. We know for sure that this cannot be a Hamiltonian system. All right, that's too bad. Let's check the other one. All right, so in the other system, again, we take the partial of f with respect to x. And when we do that, we get 3x squared plus 6 cosine of 2x plus 3y plus 0. So that's good. And the partial of g with respect to y is minus 3x squared minus 6 cosine of 2x plus 3y, right? Because we're multiplying by the derivative of the inside, plus 0. All right, so if we look at these, everything matches up. That's the same. These are the same, but with the opposite signs. Right, so indeed, it is the case that the partial of f with respect to x is equal to negative the partial of g with respect to y. So this one is Hamiltonian. All right, great. So now we can continue with the set of equations on the right. It is Hamiltonian, but we have not found the Hamiltonian function yet. We're going to do that by taking the fact that we know that that f is the derivative of the Hamiltonian with respect to y, and that g is negative the derivative of the Hamiltonian with respect to x. And we'll take the antiderivative with respect to the appropriate thing, compare what we get, and then we'll get ourselves a Hamiltonian. This is, again, exactly what you were doing when you were doing exact equations a couple of months ago. So should be pretty familiar with it. Of course, it's been a while, so this is a good reminder. It'll probably be on the final, so good thing to take a look at. All right, so let's figure out what our things are that we have. So we know, so again, right now I'll take a pause. Try this out. Try to find the Hamiltonian yourself and come back and see if your work agrees with mine. Okay, so let's see what we get. Well, first of all, we know that the partial of h with respect to y, by the definition of Hamiltonian, we know there is a Hamiltonian, its partial with respect to y will be equal to f of x comma y, which is x cubed plus 3 sine of 2x plus 3y plus 4. So that means that h will be equal to the antiderivative of that function with respect to y. And that will be x cubed y plus, minus cosine of 2x plus 3y plus 4y. And then because we normally would have plus a constant, but because this is only the antiderivative with respect to y, the constant function could be any function of x at all. Those would all have derivative 0 with respect to y. Okay, cool. So that's one. Now let's see about the other side. On the other side, we have that the partial of h with respect to x will be equal to negative g. So that will be equal to 3x squared y minus 2 sine. I'm looking in the wrong places here. Sine plus 2 sine of 2x plus 3y minus 1. Okay, so we need to take the antiderivative of that. H is equal to the antiderivative of 3x squared y plus 2 sine of 2x plus 3y minus 1 dx. All right, so I've just taken the negative sign through everything up here. That's why everything gets the reverse sign. All right, antiderivatives are, okay, we're going with respect to x now, so that's going to be x cubed y minus cosine of 2x plus 3y minus x plus some function q of y. Now, what we need to do is compare. We need these two functions to be the same because they are both h, right? So these have to match. Now, a lot of things do match. We have the same x cubed y in each of these. We have the same minus cosine term. But we have these straggling parts. We have a 4y here. We have a minus x here. To make them match, we're going to need to set p is going to have to be equal to minus x. xq is going to have to be equal to 4y. And when we do that, we get the full Hamiltonian. H of x comma y is x cubed y minus cosine of 2x plus 3y plus 4y minus x. Right? And that is the Hamiltonian of this system. That equal to a constant is a conservation law for this system. Now, I wouldn't want to have to plot that thing in the phase plane, but you can certainly do it, or you can get a computer to do it. Having that means that you can understand the behavior of the system, you can look at the phase plane, you can look at the level curves of this Hamiltonian, and know how the system behaves without actually solving the differential equation at all. Or in a way, this Hamiltonian is the solution of the differential equation. It's just not an explicit solution. It's an implicit solution where the x's and y's are all mixed up together. You take this function equals a constant, and you have a solution of this system. Okay, hopefully that clarifies things a little bit.